Good everyone. Today I'm going to talk about understanding scientific computing. Now, to understand the basics of scientific computing generally, we have to talk about technical computing, which has two branches. And I can define technical computing as the use of computational methods and algorithms to analyze, model, and solve complex problems in various technical fields, such as engineering, science, so on and so forth. So that's the basics of technical computing. Then it has two branches, which is machine learning and scientific computing. Machine learning, over the years, human learn from their past experience, while machine learn by following human instructions. Just like if I make a mistake yesterday, as I made that mistake, whatever action or whatever decision I'm going to take is going to be based on my past experience or what the knowledge I have concerning that particular thing. So human learn from their past experience generally. But machines they obey human instructions because they were built by humans. But later on, we started understanding that we can find a way or a way to actually make this machine to learn just like us. Just like the way I learned from my past experience, you learn from your past experience. That's how these machines could also learn from their own past experience. So if we could make, we making that this particular thing possible is what we refer to as machine learning. Today, many machines are proving to make this a concern, a thing of the past. Most app features use machine learning as a means to provide better services for their target audience. Just like so many apps that we have today, these apps, for example, now maybe I'm watching a movie on Netflix. Netflix is going to give me movie recommendations on my past movie views. Whatever I'm into, whatever genre of film I'm into, you see that Netflix is going to give me more recommendations from that particular genre. So that's just about machine learning. And and also these machines, there are various ways that they do learn. They learn by supervised learning, unsupervised learning, and reinforcement learning also. When I talk about supervised learning, I'm talking about the situation whereby these machines actually learn from labeled diagrams. They learn from things that are labeled. But when we talk about unsupervised, it is unlabeled. They're actually unlabeled diagrams. For example, Facebook will give you, will know your friends through the photos in your phone. You will give you recommendations from your friends. He learns from labeled diagrams. Then Netflix now is going to give you movie recommendations from what you have learned from the past. That's what we call unsupervised learning. Because unsupervised learning is that you train the algorithms on unlabeled data to discover patterns, relationships, or groupings. So they are going to understand patterns. They're going to understand patterns in which you watch that film, and then they're going to give you recommendations on it. And then we have reinforcement learning. That is to make decisions based on rewards or penalties. For example, I am analyzing bank data on whether there is anything like deceit or corruption in their results. So reinforcement learning, that's the type of reinforcement learning. It is actually based on results that we get based on rewards and penalties. Then another aspect of technical computing, we have scientific computing. Now, Julia is actually a programming language which supports mental programming, and as a result, it's specially built language used for scientific computing. Now, mental programming treats code as data, unlike conventional programming, which treats code and data as distinct features. Now, before moving forward, we'll see that scientific computing is actually a field that uses computational methods and algorithms to analyze, model, and simulate complex scientific problems. It's a multidisciplinary field that combines computer science, mathematics, and domain-specific knowledge to solve real-world problems. Now, in scientific computing, we, Julia is a programming language that was used for it because in meta programming it actually treats code and data like they are the same thing. But when we talk about conventional programming, code and data are distinct features, they are not the same. So because of this, because it treats code and data as distinct features, conventional programming is not actually required with scientific computing, but meta programming which treats code and data as the same thing. Then Julia was supports this meta programming that we're talking about. So that is why it is especially used for scientific computing. And meta programming is actually a basic tool for in scientific computing. And Julia is one paramount programming language that actually supports it. So that's why it's used in scientific computing. Now, when we're talking about serial coding, it's a fundamental concept in scientific computing and understanding. It is crucial for efficient and effective programming. Now, it's a process of executing a program of code sequentially. It executes sequentially, that is one instruction at a time. It completes one task before going on to the next task. So that's what serial coding is all about. So the process of executing a program sequentially, one instruction at a time, is what we refer to as serial coding. Now, one of the characteristics that we can note from this particular definition that was given is sequential execution. It executes its program one instruction at a time, single core processing. Only one CPU core is used to execute the code. So one CPU core for one particular program. So that's about serial coding. So if it executes a program sequentially, that will say concurrency is actually removed. There is no parallelism in serial coding. That's what we're going to be talking about next. So there is no parallelism. That's another basic characteristics of serial coding. Then what are the advantages? The benefits of actually doing this serial code is it is easy to implement. It is straightforward to understand and implement. The bugging is actually simple and you can actually predict its performance. That's about serial coding. Then we have disadvantage. One disadvantage is that limited scalability. It can become bottleneck as problem sizes increase, inefficient use of resources, long execution of time, so on and so forth. Then what are these applications? It is suitable for small scale problems that don't require massive computational resources, prototyping and educational purposes. That is, serial code is often taught in introductory program courses due to its simplicity. Now, parallel computing. We just talked about serial coding. Parallel computing is a technique where multiple processing units which work together to solve a problem or perform a task simultaneously. In serial coding, we saw that these tasks are being executed sequentially, that is one at a time, and it mainly uses one processing unit for the task. Uses one processing unit. This is where parallelism comes in. So it's a type of technique. We use multiple processing units which work together to solve a problem or perform a task simultaneously. But mind you, I would like to say that parallelism is actually different from concurrency in the sense that parallelism, we actually solve the problems simultaneously together. For example, now I have 5 tasks. I'll be solving the 5 tasks at the same time. That's what parallelism is about. But concurrency, though concurrency is still simultaneously, but concurrency does not solve it at the same time simultaneously. If I have 5 tasks, it will just move from one and then go and solve the other one and then move, and it will just look as if it's solving it at the same time. Meanwhile, it's not solving it at the same time. So that's the difference between parallelism and concurrency. I would like to use an example to illustrate the basic difference of parallelism and concurrency. For example, now, a chef he has multiple foods that he wants to prepare. So this chef is just in the kitchen now, and he's preparing all of this food. He's preparing this one, then go to the next one, then go to the next one, moving between them swiftly. So when he's moving between them, that's what concurrency is about. though it's doing them simultaneously, but it's doing one task at a time. Then when we talk about parallelism, then we have many chefs. Many chefs, and they are cooking at the same time. What are they doing? They are cooking different foods at the same time. So that is parallelism. And if we notice in this example that we gave, the chef that was actually cooking when it was only just chef, he was actually using one material. That is the one processing unit here. He's using one processing unit. But when it was many chefs, they were using their own materials, their own things. So with parallelism, we actually use multiple processing units. But in concurrency, we use single processing unit, just like in serial coding. But the only difference between serial coding and concurrency is that serial coding executes its program sequentially, while parallelism, concurrency actually executes its program simultaneously. So that is the difference between serial coding, concurrency, and parallelism. Then scientific machine learning. Now, we talked about machine learning and we talked about scientific computing. I said that Julia was actually a basic programming language that was actually a scientific program. But machine learning has been hyped all over the years. So there is a way we can actually merge the two together. That is bringing about scientific machine learning, which can be abbreviated to XCIML. That is scientific machine learning. It's an interdisciplinary field that leverages machine learning techniques to analyze, model, and simulate complex scientific phenomena. Now, we are actually introducing machine learning techniques now into scientific computing to analyze, model, and simulate scientific phenomena. What could be all these phenomena? It includes weather forecast, climate modeling, fluid dynamics, so on and so forth. So this is an interdisciplinary field that is now talking about both scientific computing and machine learning. So it's rapidly growing field that combines machine learning with scientific computing.
Check your settings.
Key characteristics of this particular definition I'm talking about. Interdisciplinary, that is, it combines machine learning, scientific computing, and domain-specific knowledge together. It's complex system, focuses on complex, non-linear systems with high-dimensional data. The physics informed. XCIML incorporate physical laws, constraints, and domain expertise into ML models, and high-performance computing also requires large-scale simulation, parallel computing, and then optimized algorithms. Now, what are its applications? What are its applications? The applications are used in climate modeling, predicting climate patterns, material science, fluid dynamics, like I said earlier, astrophysics, so on and so forth. So, what are now the challenges of this scientific machine learning? Interpretability. Understanding ML models in the context of scientific phenomena is not actually interpretable. So that's one challenge that we face with scientific machine learning. It's not interpretable, and uncertainty quantification, quantifying uncertainty in ML predictions, and then ensuring that is the data quality, ensuring high quality relevant data for ML models, scalability, scaling ML algorithms to large complex scientific programs. One thing we saw as a disadvantage of serial coding was actually this scalability. And then it's also here again as another limitation or a challenge of scientific machine learning. And mind you, in this scientific machine learning, the data required to actually solve all of these problems or perform all of these tasks is not usually there for us. So that's why data quality is actually one problem that people in the field of scientific machine learning actually face. So the data is not actually readily available because it needs more data, a lot of data. So that is one challenge in scientific machine learning. Then physics informed learning. Now, introducing physics informed learning to what we discussed recently about scientific machine learning, it actually tried to counter those effects, those challenges and limitations that we actually faced today. Now, physics informed learning is a subset of scientific machine learning that incorporates physical laws and constraints into ML, that is machine learning models. Into machine learning models. Now, what are the key concepts? That is physical laws. First of all, I'm going to talk about physical laws. The physical laws, like such as preservation of energy, momentum, so on and so forth, they are introducing it now into machine learning. Differential equations. We use differential equations to actually describe complex physical systems. The neural networks are also used in regularization, using physical laws of regularization terms to constrain machine learning. Now, it has what are the type of neural network that incorporates physical laws into the learning process. What are its applications? We see its applications also include dynamics. Remember, it's a subset of scientific machine learning. So, it's find application in material science, fluid dynamics, and also climate modeling to understand climate, to predict climate. So that's one. But what are its benefits? Improve accuracy. Remember that one challenge and limitations of scientific machine learning was it was uninterpretable. It was not, it we could not actually, it's not understandable. So introducing physics informed learning actually makes it more accurate. It makes it more understandable. So it actually counters the effect of interpretability in scientific machine learning. And also use efficient data. Now the data that was data quality was seen that in scientific machine learning was not enough. The data was not enough. So it actually posed threats, actually posed limitations to people in the scientific machine learning field. So, but what physics informed learning do? It helps in making sure that there is that it's actually interpretable and that the quality of data for scientific machine learning is provided. So that's one, that's why it's actually important. Next, we're going to be talking about ODEs. Now, what are ODEs? The full meaning of ODE is actually ordinary differential equation. And we see that in scientific machine learning, ordinary differential equations are actually introduced. There are one basic two in it. Okay, so there are differential equations that describe how a quantity changes over time or space. Now, what are the key characteristics? It is ordinary, that is, all these involve ordinary derivatives as opposed to partial derivatives. They will have differential, describe how one quantity changes over another, and then there's an equation that relates the derivative of a quantity to the other. We have different types of ODEs. There are initial value problems, boundary value problems, and then steep ODEs. Its application, one basic application. We'll see the application in physics, we can see it in chemistry, we can see it in engineering, and also in biology. So there are mathematical equations that describe how a quantity changes over time and space. It has application in many fields, especially physics. That's why physics informed learning is actually introduced into scientific machine. So a numerical method used for solving ODEs is the Euler's method. We have so many methods that are used in this in ODEs for solving ordinary differential equations. We have so many, but one basic one is actually Euler. We have branch, quarter, multi-step, and implicit. So in numerical method for solving ODEs, there are more, but I just put the Euler's method. It's actually one basic method that was used. We have IDE. IDE is another thing, meaning integrated development environment. Is a software application that provides a comprehensive set of tools for writing, debugging, and optimizing code. There are set of tools for debugging, for writing codes. Now, in scientific computing, just like what I'm saying, I can use VS Code for as an IDE to write my code or debug or optimize it. And then some benefits of using IDEs is improved productivity, better code quality, as well as enhanced collaboration and simplified coding. So introducing IDE or using IDE actually makes performance more accurate and it enhances it. So that's all. Thank you.
Questions?
Is Julia the only programming language that is used in scientific computing?
The only. Yeah, I'll say yes. I'll say yes. Yes, because like I said earlier, it's one programming language that actually supports meta programming. So if there is any other programming language that actually supports meta programming, then it can actually be used. But one basic programming language for and that's just built especially for it is Julia.
In terms of IDE, you can use anyone, right?
Yeah, you can use anyone. You can use anyone. It's not just restricted to just this. You can use anyone. Any other question?
You said you were using some saying something about chefs. Could you explain that?
Chefs.
Yes, like you're using chefs as an example.
Okay. I was actually describing the difference between parallelism, serial coding, and concurrency. I said serial coding is actually, it performs tasks sequentially. There is one after it in different orders. I will complete this task first before going to the next task. So I said that it does not solve tasks concurrently. So when I went to parallelism, I said parallelism actually solve it concurrently or simultaneously. But there's actually a difference between when we say concurrency and parallelism. When we say concurrency, the main similarity between concurrency and parallelism is that they solve problems simultaneously. But the difference is that they use different units, processing units. And parallelism will solve it the same time. For example, if I'm doing 5 operations now, I'll do it together with 5 operations. But concurrency will just move between these 5 operations swiftly that you never notice that it is doing one at a time. So that's why I use that chef. Now, for example, now one chef is actually cooking 5 foods. So what that chef is going to do is going to move from this food. Then when maybe this one is stable, we'll go to the next one, then we'll move it to the next one. So that is going to do and make sure that that 5 food is prepared, and it's going to use one set of materials to actually prepare that 5 food. The spoon is going to save. But when we have many chefs, that each chef to one food, you see that everything will be happening simultaneously together at the same time, not just one person that is using it. So that's what I was saying. Okay, any question? Any other question? Okay.